All right. Any other questions about that particular reaction? All right, and it's the we're going to do a couple of examples just to kind of drive the point home. But let's look at the next example. Right here. You're doing the same reaction, so you're adding bromine to the ring, but the difference is now you have an electron acceptor, or what we call an electron withdrawing group, right? And that's over here too. All right, so you have an acceptor on the ring, and all acceptors are meta directors, right? So if you look at the product, you can see that the bromine is in the meta position this time, right? Because of the group that's on there. So what are some examples of acceptors? Let me erase some of this stuff. Right, some examples of acceptors are carbonyls, right? Any type of pi bond attached to a ring can act as acceptors, right? Whether it's a carbonyl or alkene or alkyne, it doesn't matter. Nitro groups are great acceptors, right? Sulfonyl groups are great acceptors. So your acceptor is anything that can accept a pair of electrons, either by resonance or by induction, right? Anything that can pull away electron density from the ring, either by resonance or induction. All right. And so when you put an acceptor on the ring, what we say is that the ring is deactivated. Right. And when you put a donor on the ring, we say the ring is activated. And this is for electrophilic aromatic substitution. If you're doing nucleophilic aromatic substitution, where the ring is the electrophile, then it's the opposite. But for this electrophilic aromatic substitution, we say that the ring is activated if you put a donor on the ring, and then we say it's deactivated if you put an acceptor on the ring. All right. Any questions about donors, acceptors, anything like that? No question. All right. Let's do a couple of examples. So let's say I have a reaction like that. What kind of reaction is that, first of all? And then the other question, second question is, what's the product going to look like? Is it so we've only done three reactions, right? Acylation, alkylation, or halogenation. Because the other two reactions, the nitration and sulfonation, even though we didn't cover them, they're not. We didn't talk about the mechanism because they're not overly complicated. Right? It's just.
Is
But
this
I would rather have focused on the main three reactions. So, what out of the three reactions that we talked about, which one is this one?
would this be isolation?
It's an acylation.
Isolation.
Mm-hmm. What that means is that I'm adding in this carbonyl group, not the chlorine, right? Just the carbonyl group. So what's the product? You know it's gonna have a benzene ring, right? Is the product gonna have this carbonyl attached at that carbon somewhere on the ring?
Yeah.
Yep.
Yeah, it's gonna be right. We'll put it right here. Let me get the right color pen. We're gonna put it right there. Is that right? Anybody disagree with that? Or got something different other than being at a different carbon on the ring? All right. So let's take that product and let's let me do it a little different. Let's add a bromine to it. What do you think? Now the question, see the ring is substituted now. But is it substituted with a donor or an acceptor? Is a carbonyl group, and this is just, is a carbonyl group a donor or an acceptor?
Donor.
So a donor donates electrons, is that right?
Right.
Where the electrons going to come from in the carbonyl?
Would it come from that oxygen double bond?
Let's see. So we're going to put two lone pairs on oxygen. But do they have somewhere to go? If I push them anywhere, or if I push them there, that's going to put too many bonds on carbon, on this carbon. Let's think about the carbonyl now. We know this is one thing we do know about it. It's got a big dipole going that way. So the carbon is partially positive and the oxygen is partially negative. So what do you think now? If the carbon is the part that's attached to the ring, is it a donor or is it an acceptor? And you got a partially positive carbon on the ring. It should be an acceptor, right? Can I do this? Let me see if this will help you. Can I do this? Can I do resonance like that?
Yes.
Yeah, I can. So that makes that an acceptor. All right. So if it's an acceptor, what kind of directing effects is it going to have on the incoming bromine? Is it going to be a ortho director, a meta director, or a para director? All right, let's go back up to the top. All right, all of your acceptors or electron withdrawing groups are meta directors, and then your donors are ortho para directors. So if I put an acceptor on the ring and then do another reaction on it, right? That acceptor should make the product meta. So the product should look like this. And tell me if you agree or disagree, or if you're just not catching it. Anybody disagree with that?
Do you mind showing the mechanism for it? Like with the bromine? Come in.
So the mechanism is the same 3 steps, right? The bromine is going to coordinate to iron bromide. But the problem is, like with the metal director, the reason why we say it's deactivating is because those para positions, the para and the ortho position, are not. There's no electron density there. Let me show you why. All right, let me do this first before we do the mechanism. So if I do, I'm just going to put an R group. If I drew this and I drew the resonance form for it, is this what the resonance form is going to look like? Is that the resonance form based on the arrows I just put in?
Yeah.
All right. So to answer this question, if the ortho site is positive, can I add an electrophile there?
No.
I cannot. Right? No electrophiles can come here. Because in order to add an electrophile, you got to give it some electrons. Is that right?
Mm-hmm.
So then if I draw the next resonance form, where I shift that pi bond over, that's going to look like this, isn't it? Sloppy, my bad. Right, that's the next resonance form, is that right?
Yeah.
You see where the plus charge is? It's on the para position. Is that right?
Mm-hmm.
So if that's the case, I can't add an electrophile there either. Right, you don't have any electrons at para or ortho. But if you notice at the meta position, you actually do right have that pi bond that can be used as a pair of electrons. Does that make sense?
Yeah.
So does that clear up why it only add at the meta position, or do you still want to see the mechanism?
Oh no, that cleared it up.
Okay, all right. So that's what I'm saying. If you know the difference in an acceptor and a donor, then that'll give you a clue as to which product you're going to use. All right. Let's do another example. Let's do I forgot to tell y'all about this one too. All right, that's phenol. That's another common um, benzene derivative, right? And it goes by its common name. So let's take that plus let's do that. Now oxygen on phenol has lone pairs. Is that right?